Thanks so much. And first, I'd like to thank the organizers for this opportunity to speak, and I'd like to thank all of you for what has been an amazing week. Thank you so much for everyone who's spoken and been a part of this workshop. And also, just to start off, happy Pride Month to you from me and my family. This is me, my husband Bill, our son Ben, and our dog Roscoe. So today's talk is a little bit of a mashup between something that I've been working on recently, which is Mukai models of MG-bar, and something I worked on a long time ago, which was equations of curves with many automorphisms. And this spring I thought, sort of for a lark, I wonder what some of the curves with automorphisms look like in Mukai's models. And it turned out to be interesting and beautiful, and I'm going to tell you more about it today. So first, just a little bit of background on automorphisms of curves or Riemann surfaces. So let C be a compact connected Riemann surface of genus G, or equivalently, a smooth projective algebraic curve over the complex numbers. And just starting very generally, how many automorphisms can C have? And so if we start in genus 0, well, the only smooth genus 0 curve is P1, and we know the automorphism group is PGL2C, which is a three-dimensional group. Genus 1, your curve is a complex torus, so it has a one-dimensional group of automorphisms. But once you get to genus 2 or larger, the automorphism group is automatically finite. So that is a 19th century result due to Schwartz. In fact, we have an upper bound for the size of the automorphism group. It's 84 times G minus 1. That's due to Hurwitz, again, 19th century. And if the genus is at least 3, then we can know that in general, having any non-trivial automorphisms at all is a really special thing. So most curves have no automorphisms. And so whenever we have curves with lots of automorphisms, they're special and almost always beautiful, in my opinion. And the last thing I want to note is, so Hurwitz has this bound 84 G minus 1, and you can reach that bound for some values of the genus, but there's other values of the genus where you don't get anywhere close to that. Okay, and so we don't always get to 84 G minus 1. Okay, so next I was going to review a list of some of the curves of low genus that have the most automorphisms. And then some point later, I realized there's actually a really handy table in Wikipedia. So following many other speakers, I've stolen a page from Wikipedia here. The title is Hurwitz's automorphisms theorem. And again, you can click and get equations for all these things. So, in genus 2, it's the hyperelliptic curve, which is branched over the 6 points on the sphere given by the vertices of an octahedron. In genus 3, it's the Klein-Quartic, and its equation is x cubed times y plus y cubed times z plus z cubed times x equals 0, and so on and so forth. And my main comment about this slide is just to say that everything in genus 2 through 6 was already known by the year 1900. People knew that these curves had these automorphism groups, and they even knew that these were the curves for those values of the genus that had the most automorphisms. And so, by the way, they've already conveniently marked it for us here. So in genus 3, you actually get to 84 G minus 1 with a Klein-Quartic. But for genus 4, 5, and 6, the largest automorphism groups are strictly smaller than 84 times G minus 1. So already by the year 1900, Fricke had proved that there was a genus 7 Riemann surface that had 504 automorphisms. But we didn't get an algebraic description of that curve until much later. In 1965, Macbeth proved derived a set of actual algebraic equations describing the canonical ideal of this genus 7 curve. So for a general genus 7 curve, you expect that the canonical ideal should be generated by 10 quadrics in 7 variables, and here they are. Here, zeta 7 is e to the 2 pi I over 7. These coefficients a sub j are given by some differences of 7th roots of unity. Okay, so there's a lot of things that I like about these equations. So a few comments. First of all, in the first line, you get the sum of squares. So that tells you right away that this curve is not going to have any real or therefore rational points at all. Second, just from the structure of these equations, you can work out pretty easily what the Galois group does to these equations if you replace zeta 7 by another primitive seventh root of unity. And I guess one more feature that I like about these equations is that at least this group of equations are just given by trinomials, but these others have 7 terms each. One last property that's pretty nice is that the automorphisms of the curve as sort of elements of GL7 have a really nice structure for the set of coordinates that Macbeth used. So the automorphism group is generated by an order 2 diagonal matrix. And this 7 by 7 matrix, which ends up having order 3. Like I said, by 1965, thinking back to that Wikipedia table, we knew all those curves and we had equations for all of them, and we knew exactly how the automorphism groups acted on those varieties. All right, a little more modern, moving into the 21st century now. People discovered rational models of the Fricke-Macbeth curve in genus 7. And so I learned about this in a paper by Top and Verschoor, where they exhibit equations for 2 rational models of the Fricke-Macbeth curve. One is due to Brock circa 2004, and another is due to Hendricks circa 2013. And I think Hendricks appears in his dissertation, but Brock's work was sort of never published and just circulated among experts until Top and Verschoor publishing attributed it to him. So here we have another set of 10 quadrics in 7 variables that also give us a curve with 504 automorphisms. And this set of quadrics has some different properties than Macbeth's set of equations. All right, so you can see they're all trinomials. If you dig a little bit deeper, you'll notice that there's no y2 squared and no y4 squared. So that tells you that the basis vectors e2 and e4 give you rational points on this curve. So there's a lot of things I like about this, but one thing that you pay the price for getting to these nice equations is that the automorphisms are terrible in this basis. Okay, so I couldn't even print the matrix giving you the coordinate change between Macbeth's coordinates and Brock's. I had to do it as a product of 2 matrices to get it to fit on this slide. But you can imagine that if you multiply these matrices together, you're going to get something messy. And when you conjugate the automorphisms I showed you for Macbeth's curve, it's not something you need to see. Okay, so we get so we get these nice equations, and the price we pay is that the automorphisms look terrible. Okay, so here's the question I asked. What would things look like if we adopt Mukai's approach to genus 7 curves? And so let me describe how he thinks about genus 7 curves in a couple of slides. So for a smooth genus 7 curve, and by smooth I mean it's not hyperelliptic or trigonal or tetragonal, Mukai showed that the multiplication map going from a pair of quadrics in the ideal, the canonical ideal that is, evaluated as elements of I4 has a one-dimensional kernel. So let Q be a generator of that kernel. And so, since it's an element of sim2 I2, that means you can think of it as a quadratic form on the dual vector space I2 check. Okay, and so what should you do when mathematics hands you a quadratic vector space? You should look for isotropic subspaces, and in particular the largest ones you can find, which are the Lagrangians. Okay, so again, I2 is a 10-dimensional vector space with 10 quadrics. And so half-dimensional is going to be a 5-dimensional subspace of that 10-dimensional vector space. And you poke around and you ask, where could I possibly come up with Lagrangian subspaces of this 10-dimensional vector space? And you don't have to look too hard. And the answer is, if you look at the Jacobian matrix of any point on your curve is going to be, the row space of that matrix is going to be a 5-dimensional vector space, and it's isotropic for this quadratic form. And so we can produce lots and lots of Lagrangians from this construction. And so Mukai's notation for this is WP perp. And so the idea is you pick any point on your curve and you form the row space of this Jacobian matrix to get a Lagrangian for this quadratic form. Oh, whoops, I think I skipped a slide. Hold on. Oh, no, I didn't. Okay. Now, there is a algebraic variety called the orthogonal Grassmannian that parameterizes Lagrangian subspaces of a fixed quadratic space. So inside the Grassmannian of n-dimensional subspaces of a 2 n-dimensional vector space, when you have a quadratic form, there's a subvariety called the orthogonal Grassmannian that parameterizes just the Lagrangian ones. And so in particular, we're interested in 5-dimensional Lagrangians in a 10-dimensional quadratic space. So that's OG 510. And that happens to embed into P15. This is using the so-called spin representation of the orthogonal group O10. And Mukai's coordinates for this P15 are given by x's with subsets of even size. And so it can, for those of you who know about spin representations, this is the even Clifford algebra on 5 elements. And here are the equations of the orthogonal Grassmannian. And my main point here is just to show you that they look nice. Okay. So here's Mukai's main theorems. So when C is a general smooth genus of curve, so again, not hyperelliptic, trigonal, or tetragonal, this map that takes any points to its Lagrangian, and you can think of that Lagrangian as a point in the orthogonal Grassmannian, is an embedding of your curve into the Grassmannian. Moreover, the numerics work out just right, that curve should actually be canonically embedded in P15, which means that it actually lies in some 6-dimensional projective space inside P15. And so your curve is a linear section of some projective space P of dimension 6 with your orthogonal Grassmannian. Okay. And so I have another recent paper where I was thinking about Mukai's models and these kinds of things. But earlier this spring, I thought, oh, I wonder if I can find the linear space that gives me the frickin' Macbeth curve, which was one of my favorite genus 7 curves, or one of its rational models. So here goes. You can actually follow through Mukai's construction as an algorithm to get the answer you're looking for in this case. So what are the inputs we need? Well, we need the quadrics defining the canonical ideal of C. We've got those thanks to Macbeth and Brock and Hendricks. And I also need to choose 8 points in general position on my curve. And then once I have that, here's what I can do. Well, first you need to compute the quadratic form that we're supposed to work with. So compute the multiplication map and its kernel. You'll probably get something that isn't exactly the quadratic form that everybody likes to use in textbooks. And so you might need to diagonalize that a little bit by adjusting your basis of I2. Next, you want to compute the Lagrangians of each of your points by evaluating the Jacobian matrix and getting that row space. And then you want to find those Lagrangians as points in the orthogonal Grassmannian. And there you're computing something called the spin area of your Lagrangian. And again, this is all in Fulton and Harris's a book on representation theory. And so you can do all those calculations with a computer. And now take your first 7 points. Their span is the projective space that you're looking for. And if you intersect that projective space with your orthogonal Grassmannian, you should get the curve you started with. And you can actually check all of that if you use your 8th point. And so this is a generalization of the fact that, if you have 3 points in P1, there's, two sets of 3 points in P1, there's a unique element of PGL2 mapping the first set of 3 points to the second set of 3 points. Well, here, instead of n equals 1, we're doing n equals 6. And so if you have 8 points in P6, there's a unique element of PGL7 that takes one to the other. And so you can use your 8th point to build this isomorphism and check your work. Okay, so I did all of that, and I'm just going to make a few quick comments on what happens. So in step 1, I computed the multiplication map in its kernel, and the thing I got, luckily for me, was equivalent over the rational numbers to the quadratic form that Fulton and Harris use in their textbook. Okay, so that step went just fine. Next, I needed some points on my curve so that I could evaluate the Jacobian matrix. Well, I mentioned Brock's curve has 2 rational points, but as far as I know, that's all. And so what I did is I used the fixed points of the automorphism group to get some more Q zeta 7 bar points on my curve. And so I had to move to a larger field. However, after I computed those Lagrangians and their spinors and took the span, the plane that I got was actually defined by rational equations. So I was back in Q. And when I computed the isomorphism that took me back to Brock's model, it turned out that that map was also defined over Q as well. So in the middle, it wasn't sure how things were going to turn out at the end, but in the end, we actually got Brock's model or something that's equivalent over Q to Brock's model. And here are the equations. So on the right, I have equations in the x variables between each other. So these are defining sorry, how many equations do I have? These 9 hyperplanes are cutting out my P6 inside of P15. And so that P6 intersected with the orthogonal Grassmannian, I claim, is giving you Brock's model. And over here, these are the variables that I'm using as variables on my P6. And I'm telling you an isomorphism of the P6 that I've defined inside P15 back to Brock's coordinates with these equations. And you can see everything worked out really, really nicely. So these are, in my opinion, the nicest equations I've seen yet of the frickin' magnetic curve in genus 7. Okay, going very quickly. All right, genus 7, that worked really well. After I gave this talk at AMS sectional in Boston in the spring, someone wrote to me a week later and asked, hey, what can you say about genus 8? And so I pulled out some old computer code I had, and I came up with equations for the genus 8 curve with the most automorphisms. Here they are as quadrics. And then I played this game as well. Mukai has a different approach to genus 8 curves, but I found hyperplanes cutting out this time a P7 that when intersected with the Grassmannian GR26 and its Plucher embedding gives you the genus 8 curve with the most automorphisms. And again, the equations are really, really nice. All right, skipping ahead, genus 9, same thing. I found with quadrics, not going to print them. But when you look in Mukai's model, the equations come out as nice as could be. Remember what I said though, when the equations look this nice, the automorphisms generally look terrible. They're really, really horrible in the spaces. Okay, and then lastly, genus 10, I have the quadrics as well. So just to summarize, Wikipedia is telling you that we have equations for the curves with automorphisms going up to genus 7. And I'm claiming that when I publish this work, we'll be able to add 3 more entries to this table. So thank you very much.